Hello, Math 120, and this is Professor Gonzalez, and I would like to do some problems from get my pencil set, homework problems from 7.1. Now, 7.1 takes a look at the square root property. The square root property. Let me write that down. So the square root property basically says that if you have, let's say, x squared, and that equals, let's say, I'll just keep it easy, 25. We're going to go ahead and square root. Square root property says you could square root both sides of the equation, but when you do that, there's going to be more than one solution. Once again, the square root undoes, whereas the inverse of squaring. So we're left with x, but we have to be careful because there are going to be two possible solutions, plus or minus square root of 5. Now you can see that when we check it, right? Because the original problem was x squared equals 25 if we're going to run a check on that. And, if you put a 5 in there, that's the obvious one that everybody gets. Yeah, 5 squared, 5 times 5 is 25. So that would check with the right, left and right. The one that students forget about is the negative answer because of the squaring property, right? When you square something, square a negative, it becomes positive. So negative 5 times negative 5 is also 25. And so that would show that we're going to get two solutions. So the square root property is basically saying if you're going to square root both sides of the equation, don't forget that you're going to get two solutions. There's a little more to it than that. Like if you had x squared equals 0, you're going to get 1. You can't have plus or minus 0, so that wouldn't be two solutions, I guess. And also, when you're square rooting a negative, in the past that was a problem, but now we have imaginary numbers, complex number system, so that wouldn't be a problem either. Okay, let's go ahead and get started. Number 1 is going to do a step-by-step solution here. It says isolate the expression containing the square root. No, the square term rather. So how would we isolate that? Well, we isolate it just by subtracting it out or adding out in this case. So we're just going to add a 169, right? Because we're doing the opposite of subtracting 169. So we add 169 to both sides, and that gives us s squared equals 169. Step 2, use the square root property. Don't forget the plus or minus symbol. Yeah, don't forget the plus or minus symbol. So basically we see s squared, and this, once again, this is the square root property for perfect squares. S is a perfect square, right? S squared is a perfect square, rather. So if I square root both sides, I could, in effect, undo this squaring, leaving us with just an s. But we do have to remember the plus or minus situation. So we've got the square root of 169. Well, 169 is just 13 squared. So we get plus or minus 13. All right, isolate the variable if necessary. In this case, s equals plus or minus 13 is already isolated. Okay, s is the variable we want to isolate. It's already isolated. So that's good to go. Okay, verify your solutions. All right, well, we go ahead and say s equals 13. So we plug in a 13 right there. We know that 13 squared is 169. And 169 minus 169 is just going to give us 0, which is true. And over here, a negative 13 is put in as a solution. Negative 13 squared gives us that positive 169. And of course, when you subtract those two, we also get 0, which is true. 0 equals 0. All right, let's see if we can do this ourselves without a step through type of deal. Solve the equation using the square root property. We're actually solving for x here, right? So we want to undo the square. We can do that with the square root property by square rooting both sides, but never forget that you're going to get a plus or minus case with these answers. So you're going to get x. So the square root of x squared is x plus or minus, then square root of 144 is 12. Once again, 144, right, is just going to be, I guess we can write it as 12 squared. So you can see that that just simplifies to plus or minus 12. X equals plus or minus 12. If you have time, you can go ahead and check the solutions by plugging them back into the original problem. We don't really have the same problem of having extraneous solutions that we have when we square both sides. That can produce extraneous solutions. That doesn't really happen here. But you can always check your work if you have time. Make sure you didn't make a mistake. Let's take a look at the next one. We square root both sides. We never forget our plus or minus when we do that. And so therefore we get x equals, and now let's see, the square root of 112. That can factor down, prime factors, but if I can find the biggest perfect square, which is 16, 16 times 7 is 112. And so this would actually, in fact, simplify down to 4 square root of 7. So never forgetting your plus or minus, though. X equals plus or minus 4 square root of 7, and that is the answer. We move on to number 4. Now, in the past, before we had imaginary numbers or a complex number system, this would be a big trouble spot. But we're going to square root both sides. Don't forget plus or minus. And because we have imaginary numbers, imaginary unit is defined, this is no longer going to be a problem. Let's go ahead and show our work over here, negative 121. Now we could think of that as, this actually just simplifies right away using the imaginary unit and the principal square root of a imaginary, or of a negative under the radical. But anyhow, I could show it like this also, which is kind of doing the same thing, negative 1. So we know the square root of 121 is 11, and the square root of negative 1 is I. So we've got x equals plus or minus 11i. All right, next problem. Remember, we do want to isolate our perfect square. We do have a perfect square here. We need to isolate it by subtracting 5 off of both sides. So now we have x squared. I think I'm just going to put this over here for space. So now we have x squared equals 257 minus 5 is 252. Of course, we're going to square root both sides of the equation. Plus or minus, never forget that. X equals. Now we have 252, and we want to break that down and see if we could find any of the largest perfect squares in there. Once again, you could always prime factor it down. But if you could see the largest perfect square, like 36 times 7, it's just going to save some time for you in terms of simplifying. So x equals plus or minus 6 square root of 7. And there you go. All right. Okay, let's take a look at the next one. Once again, isolate your perfect square. Z squared is a perfect square. So we're going to isolate that by, not subtracting rather, but dividing both sides by 7. This gives us z squared equals 9, right? 63 divided by 7 is 9. And we square root both sides, never forgetting our plus or minus. And this is just going to give us a nice simple z equals plus or minus 3. Don't remember. Actually, I should have probably gone through and plugged these in to. I usually put them into my lab to see. If they don't have a plus or minus on that, you could always plug it in like this: a negative 3, comma positive 3. In terms of putting the solution in there. Usually in math books you put plus or minus, saves writing time and stuff like that. Let's see, number 7. Number 7, we're dividing both sides by 11. When we do that, we get x squared equals, and now this is not as nice, right? 80 over 11, and I don't see any common factors that will reduce. So then we just go ahead and take our square root of both sides. Don't forget plus or minus. And how's that going to simplify down? Well, there's a couple different ways of doing it. Here's how I'm going to do it. I'm going to go ahead and take a look at the square root of 80 and begin to break that down. Well, I know square root of 80 is just, or 80 is just 16 times 5. So square root of 16 times square root of 5. So this is 4 square root of 5. So the numerator, so I'm going to use the quotient rule for square roots, and I'm going to write it as a quotient of square roots. So it's going to be, now I'm going to take, what I'm basically doing is I'm taking 80, the square root of 80, and simplifying that down. And that's going to give me right here, I guess I'll use some color to show that. That's going to give me this new stuff right here, which is just 4 square root of 5. And then down below we have 11. And don't forget the plus or minus. Now, the denominator also, okay, I want to show an extra step here. We're using that quotient rule, which would then say the square root of the fraction 80 over 11 is now the square root of 80 divided by or over the square root of 11. So this square root must still be there. All right, now we want to rationalize the denominator. We never leave our final answer with a square root in the denominator, so we'd like to take care of business there by multiplying the denominator and numerator by the square root of 11, which when you do that, that's going to give us square root of 11 times square root of 11 is just 11. That's why we selected that, because it rationalized it for us. And up top, we've got 4, and then the square root of 5 times the square root of 11 is just the square root of 55. And 55 does not have any perfect squares in it. It just has 5 times 11, so that is not going to simplify out. And so we get x equals the answer of plus or minus 4 square root of 55 over 11. Let's take a look at the next one. And it's getting a little more complicated here. But notice there is just one term with an x squared in it. So x squared is still a perfect square, okay? If there was another term with an x, like an x squared, another term had an x in it, now we don't have a perfect square, and we have to do something very tricky, clever, I should say, maybe not too tricky, but kind of clever, to make a perfect square, something called complete the square. So in this case, x squared is a perfect square, so all we really have to do is just, isolate x squared. So we go ahead and subtract 281 on both sides. And of course, when we do that, subtracting 281 on both sides, we get 5x squared equals negative 180. Then we go ahead and divide both sides by 5. And when we do this, we get x squared equals negative 36. No problem. We can just use our square root property, square root both sides, plus or minus. The negative is not a problem because we have imaginary numbers. It's going to be plus or minus 6i. Remember, the I once again came from the negative under the radical. Next problem. Now, you might not have realized it, but 5 squared is a perfect square, right? X squared is a perfect square. But when you have a binomial, like this case, x minus 9, perfect square, that's also a perfect square. And because it's a perfect square, we can take advantage of our square root property. Let me just move this kind of out of the way over here. So we can take it, even though this looks a little more complicated, it's still this whole thing right here is raised to the second power, so it is a perfect square. So we square root the left and we square root the right, never forgetting our plus or minus. And of course, the square root undoes the square, right? So we now have x minus 9. X minus 9 equals, now let's see, plus or minus, and let's just kind of take a look at that square root of negative 12. I'm thinking of that square root of 4 times square root of 3 times the square root of negative 1, right? Square root of 4 is 2, root 3, and that negative on the radicals. And we make sure the I is outside that radical symbol. So this just becomes plus or minus 2 square root of 3i. Now solve for x by adding 9 to both sides. Adding 9 to both sides, that's a funny 9. Oh, let's see. Let's make that look a little better here. Adding 9 to both sides, as I said before. And when I do that, I end up getting x equals 9 plus or minus 2 square root of 3i. And that is my final answer. Let's take a look at the next one. Getting a little more complicated, but still, remember what we're trying to isolate. We're trying to isolate the perfect square. And that whole guy right there is a perfect square. So we just start kind of peeling away the rest of it legally to isolate it. So we add 8 to both sides. We've got 7 times the quantity of x plus 1 squared equals, what's that, 35. Whoops. Oh, what's wrong with that? All right, so that equals 35. Now, of course, we want to isolate. Still, we want to isolate the perfect square. So we are going to, of course, divide by that whole left side by 7 and the whole right by 7. Of course, you know all this stuff. And we're left with x plus 1, the quantity x plus 1 squared equals 35 divided by 7 is just 5. Now, what we have to do is square root the left, square root the right, never forgetting plus or minus. And then we come up here and we get the quantity x plus 1. Remember what happened here. The perfect square and the index of 2 undid each other, or it was an inverse, and you're left with the radicand, and that's what we have right there. So now we've got x plus 1 equals plus or minus the square root of 5. Now what we want to do is we want to subtract 1 on both sides, and that's just going to give us a negative 1 plus or minus the square root of 5. All right, and there we go. Let's take a look at this next one. It says solve the equation using the square root property. Okay, something new is happening here on this one. And so I really want to take a moment to look at something. In this particular problem, the way it is right near it, see, normally I don't know if I'd put this one first right now, but that's okay. Because sometimes this is hard to see just right from the get-go, because normally we're going to subtract 81 on both sides, and that's normally what you do. But this is we're looking for a perfect square. So this one's going to drive you a little bit crazy compared to what we're doing in the future. Let me take one little break and let me go over here, and I would like to talk about something. Let's talk about perfect squares, because perfect squares have a certain pattern. If you see the pattern, it's helpful when you're trying to do something called complete the square. So let's just go through. We have x plus 1, and actually, right, x plus 1 quantity squared, we have a nice little formula for that, so we might as well use it. That takes the first term and square it, plus 2 times the first term, x, times the second term, 3, plus that second term squared. So x plus 3 quantity squared foils out, if you like that word, to this, x squared plus 6x plus 9. Now, I want to see, I usually ask the class, I'll put 3 of these up and ask them if they can see a pattern. So I want you to think about that for a second, and let me do another one. How about x minus 5 quantity squared? You multiply all that out, you get the first term squared, the middle term is 2 times x times 5, and the last term is just plus 5 squared. So it multiplies out to x squared minus 2 times 5 is 10, minus 10x plus 25. So the big question is, what is the connection here? So I'm going to put a little line here to separate those two. What is the pattern? And there is a pattern going on, and in fact, it is kind of given away a little bit by this formula. But the pattern is, if you take a look at this linear term, this is the term, the coefficient in front of the x to the first power is 6, right? If you take that term, or that coefficient, and divide it in half, so multiply it by half or divide it by 2, that gives me a 3. And if you take that 3 and square it, guess what you get? You get the constant of 9. Perfect square trinomials have this characteristic to them. You'll see it happen here again. You take that negative 10, which is the coefficient in front of x to the first. Let's put it over here. Let's go ahead and divide it by 2, or multiply it by half, either way. We get a negative 5, we square it, and we get what? 25. So that is something that does hold true and is extremely useful coming up. But let's do this one first. And so this is like, that's why I don't like this one as much as a beginning problem. But if you look at that, that has that characteristic to it. So let's just kind of highlight that, right? You take negative 8 and someone comes along and cuts it in half, which equals 4, negative 4 by the way, and then you square that, and what do you get? You get 16. This thing is a perfect square trinomial, and so it factors down to x. And by the way, I'm going to point this out every time. Don't look too hard and far when you're trying to factor these perfect squares. It's always going to be this number, base number before it gets squared. It's going to be x minus 4 quantity squared equals 81. Okay, and you can verify that, right? If you multiplied all this stuff out, you would end up getting a middle term of, or you can say what two numbers multiply to 16 and adds to a negative 8 and a negative 4 or a negative 4 multiplied gets 16 and add gives you a negative 8. So you can see that happening there. But now, what was the power of doing this? Well, we just took this trinomial and factored it down into a perfect square and showed that it's a perfect square as we factored it, which allows us to use this wonderful property called the square root property, never forgetting plus or minus. And then it simplifies this down in a real easy way. On the left, we have x minus 4. On the right, we have plus or minus 9. We go ahead and add 4 to both sides, right? Add 4. And so how do you show this stuff? Well, when you add 4 to both sides, it's going to be 4 plus or minus 9. And being that 4 and 9 can be combined together, you need to simplify that further. So you're going to have x equals, let's first take the plus symbol. So x equals 4 plus 9, which means x equals, what's that, 13? And the other symbol is using the minus sign, so I think I'll do this. We use a plus sign, and then we have to use the minus sign. So it's going to be x equals 4 minus 9, and 4 minus 9 gives us a negative 5. So you can see we get two answers here. Okay, and that was for what? Number 11. So we end up getting x equals 13 or x equals negative 5. Okay. Now they're kind of getting us used to this idea a little by little. Complete the square. So that's a big deal right there. Complete the square. And I'm kind of prepping you on this, how to complete the square. Complete the square. I was prepping you on completing the square when we did this stuff over here. Where'd it go? It's all lost and gone. Yeah, right here. You take that middle term, right, cut it in half and then square it. It tells you what you need to complete the square. And let me, that language I think will be better when we look at this problem. It says complete the square, then factor the perfect square trinomial. Okay, well, the question is here, when we're completing the square, we do not know what number goes there to make a perfect square. Oh, wait a minute. Yes, we do. Because if you believe me, what happened on this little box, and I showed this little box, what do? We take that linear term in the middle, the coefficient of it, and cut it in half, and then squared it. So if I want to know what goes right here, question mark, what goes there, all I have to do is take this number, negative 26, then I cut it in half, which gives me negative 13, then I square it, and when I square that, that gives me what, 169? So 169 will complete the square. It'll make that trinomial a perfect square. The expression is, and they're asking us not to factor it yet, the expression is x squared minus 26x plus 169. And you can verify that if you're really into, this whole thing of saying what multiplies to 169 and will add to negative 26. Well, that's going to be negative 13 times negative 13 gives us 169 and adds to negative 26. So this little guy right here that we just figured out the number that makes it a perfect square, now they'd like us to factor the expression, and that should go fast for us because you don't have to look far and wide for this stuff, because it's going to be this guy right here is going to be what it factors down to. And you could even see it over here, right? There's your negative 13. This is just going to factor down to x minus 13 quantity squared. It's a perfect square. Okay, so this is the procedure of completing the square. Got to give you a little cautionary tale here. Caution sign that this procedure of taking the linear, or that middle term, the coefficient of it, cutting it in half and then squaring it and getting this number, it really only works when you have a leading coefficient of 1. So if you do not have a leading coefficient of 1, you would have to divide that leading coefficient out legally, right? You divide it on both sides of an equation. So if it's an equation, whatever you do to the left, you do to the right. So that's legal. And that's something you have to do, even if it causes nasty fractions, because this procedure requires us to do this with this a 1 in the front. Okay, so let's take a look here. At least it simplifies that procedure we just showed. So solve the quadratic equation by completing the square. All right, so number 13. Now, I do want to say something here. They are telling us we must do this by completing the square, which is a new technique. So if they didn't say complete the square, what would you normally do? Normally you would subtract 48 on both sides and then see if you can factor it. Now, that is the fastest way to solve the quadratic equation if it's factorable, right? That's pretty much the fastest way. If it's not factorable, you cannot do it that way, because this way requires us to factor, right? And that's the way we've been using. So completing the square is a new way to solve quadratics, but it works with problems that are factorable like this one, or not factorable. So just want to make that connection for you. They're asking us to complete the square, but if a problem was in fact factorable, really the fastest way probably would be just to factor it. But they're asking us to complete the square, so we're going to do it this way. So how do we complete the square? Well, you take that coefficient of that linear or middle term, 8. You cut that guy in half. That gives you 4. You square that, and that gives us 16. Now we know that x squared plus 8x, I'm going to put a little space, equals 48. And I'm going to put a little space over here, because whatever we do to the left, we must do to the right. So I'm going to add a certain amount on the left and right. Now I'm adding it on the left, that's 16, to complete the square. Why am I adding it on the right? Well, I have to keep the equation balanced. Okay, so now I know that this is a perfect square because I made it that way. I know that I don't have to look very far because it's going to factor down to that number. So don't hurt yourself. That's what I always say. Don't hurt yourself. It's always just going to be x plus 4, right? That number that's right before it gets squared. And you can verify it. What two numbers multiply to 16 and adds to 8? Well, 4 times 4 is 16. 4 plus 4 is 8. Yeah, it's definitely it. And on the right-hand side, we are going to get, what's that? 48 plus 16, which is 64. Well, that's a nice number because it's a perfect square, right? This factored down, whoops, don't forget the square, factored down to x plus 4 squared equals 64. Now that that's a perfect square, we could use our square root property, and remembering not to forget our plus or minus, and also remembering that that was a square, so I'm going to lose that. Now this simplifies down to just x plus 4 equals, and what is the square root of 64? Well, it's plus or minus 8. We go ahead and subtract 4 on both sides, so we get a negative 4 plus or minus 8. Now, make sure make sure that you simplify this further because, right, a negative 4, and I'm going to say plus 8 gives us 4. And on the other hand, a negative 4 minus 8 gives us a negative 12. Okay, so on this one, we're going to say x equals 12 or x equals negative 4. Whoops, let's see. Did I make a mistake? Let's see, this is going to be negative 4. No, this is correct. I have some notes that I wrote a little bit differently, but I think on the notes I wrote something different. Just let me verify real quick. That should be a negative 4. Yeah, this is correct. Okay, so this gives us, if we want to write it out, x equals 4 or x equals negative 12. Now, remember I was saying that this problem actually could have been done quicker because it is factorable. You know, I just want to let you know when your answers are these nice rational numbers, or I should say numbers that don't have some numbers that the square roots will always simplify to a rational number, right? 4, negative 12, these are all rational numbers. When your answers do not have like the square root of 3, right? Something that doesn't simplify, or does not have something like 3i, imaginary numbers, when they have these nice numbers, these rational numbers, it just meant that that original equation was actually factorable, right? It was actually factorable. I'm going to go ahead and show that factoring. This is not something that's required, but I'm trying to connect in your brain that what we're doing right here, solving the quadratic equation, is the same thing we did before. It's the same thing we did before, but we're using a new technique that works for non-factorable as well as factorable quadratics, and it will work for, it'll allow us to get answers that are not just rational answers, but irrational, square root of 5, square root of 7, and imaginary complex solutions. Okay, so let's take a look. We could have done this, and what was the problem again? X squared plus, it was x, I don't know why that just came up. X squared plus 8x. I'm going to go ahead and subtract 48, so I get negative 48 equals 0. So this problem, even though we're in 7-1, could have been done on a previous section when it just said factor it. What multiplies the negative 48? And so you go over here. It's okay, let's see. Negative times a positive, right? 48. What numbers are going to work for that? I don't know, maybe a 12. What's 12 times 4? 12 times 4 is 48. Okay, well, let's see. We're going to have to make a positive 12 and a negative 4 because we're looking for two numbers that multiply to negative 48 and also will add to 8. Okay, so therefore this just factored down to x. Remember, the leading coefficient is nice and easy with a 1, so it's just x minus 4 times x plus 12 equals 0. Set each factor equal to 0, so x equals x, well, if I show all my work, I guess I should, x minus 4 equals 0, so x equals 4, and set the second factor, x plus 12 equal to 0, so x equals negative 12. And notice we get the same exact answers, okay? So we just used a new technique, a high-powered technique, on something we could have actually used old techniques with, of factoring, setting equals 0 and factoring. But look at this guy. This one, if you tried to use the old technique, what multiplies to 1 and adds to negative 4? Nothing. This is prime. So as we look at this, our old technique will not even work with this problem. So our new technique is totally critical. Completing the square is the only way we can do this problem, at least up to 7.1. 7.2, we get a formula that actually allows us to do it, to use another formula to do the problem as well. But solving the quadratic by completing the square. Okay, here's how I like to do it. I collect, well, I gotta switch to that. Let's see. I collect all terms that have x's. So x squared minus 4x. I know, oh, wait. we've got to subtract the 1 out, right? So I'm going to leave a space. I subtracted 1 on both sides. So I'm leaving a space on both sides. What is that space for? That space is the number, that magic number that completes the square on the left-hand side. How do we do that? Well, we take that linear, or that term in the middle of -4. We chop it in half, -2. We square it, 4. And 4 is that number that plus 4 completes the square. Well, if I add 4 on the left, I better add 4 on the right, keep the equation balanced. And this is now a perfect square. What does it factor down to? It factors always down to that little guy right there before we squared it. And you can see that what multiplies a 4 and adds a -4, what's a -2 and a -2. So x minus 2 quantity squared equals 3. Okay, now it is a perfect square. That's awesome. So I can square root the left and square root the right. Don't forget plus or minus. And this now leaves us with x minus 2 equals plus or minus the square root of 3. Go ahead and add 2 on both sides, and we get 2 plus or minus the square root of 3. All right, add 2 on both sides, and that's it. We cannot add a 2 and an irrational number square root of 3 together. They're not like radicals, and so that's how we write our final answer. That is actually 2 answers, right? 2 plus square root of 3, and then the other one is 2 minus square root of 3. Number 15, solve the quadratic by, once again, you guessed it, completing the square. All right. Let's collect our variables. N squared minus 8n. I'm going to subtract 25 on both sides of the equation. And I'm going to leave a space there to try to figure out what's that special awesome number that completes the square. Well, I take -8, I chop it in half, and then I square it, which gives me 16. So 16 is going to complete the square. If I add 16 on the left, I better add 16 on the right. What does this factor down to? Well, it better be a perfect square. That's what I'm going for, huh? So I get n minus 4 quantity square. And where did I get that? Once again, don't look too far. It's going to be right there every single time with this procedure. And I've got a -25 plus, 16, which gives me a -9. Came from that guy. And now I square root both sides. But don't fear the negative under the radical, because we have that defined now. This is going to be n minus 4 equals plus or minus. So what is the square root of -9? It's just going to be 3i. Now this is a complex number. We must write our final answer as a complex solution. All we have to do is add 4 on both sides of the equation, right? And we get the real part is 4, and the imaginary part is plus or minus 3i. This gives us 2 solutions, 4 plus 3i. The other one is 4 minus 3i. All right. Ooh. So what makes this one tougher is, well, let me set up first. P squared minus 3p. I'm going to subtract the 3 off of both sides. And I got to figure out what special number completes the square. You're going to find out why this one is tougher in just a couple seconds. Here it goes. So what do? We take that coefficient of that linear term in the middle and we cut it in half. Well, when you have an odd coefficient, cutting in half leaves us with a dang fraction, right? So now we got to take that dang fraction and square it. And that gives us another, I don't know if it's nasty or not, but a -3/2 times -3/2 is positive 9/4. And that is what has to be added to both sides. Yikes. So this is added to the left. Now you're feeling the pain of this thing, added to the right. Well, normally if you saw a problem like that and says someone to factor it, you might say, what? I'm not factoring that with fractions. But you know, you picked these numbers, right? Didn't you pick these numbers? Because why did you pick these numbers? You picked these numbers because you knew it was going to make a perfect square. And in fact, you know that this little guy right here is what it factors down to. So instead of banging your head, you just look right there and you can see it's just negative 3 halves. So p minus 3 halves quantity squared is what that factors down to. And you could verify it. What multiplies to a 9/4? Well, how about negative 3 halves times negative 3 halves? That's 9/4. Bingo. What adds to a negative 3? Well, negative 3 halves plus a negative 3 halves is a negative 6 halves, which equals negative 3. There you go. Bingo. Middle. Okay, so these fractions, they still have to hold true, but of course fractions can be a little more challenging with these problems because you're already learning a new thing called complete the square, and then we throw fractions in there, right? But it happens. Why did it happen? It happened because we had an odd linear coefficient right there. Well, now we're going to have to add those two together on number, what's this, number 16. And, it shouldn't be too hard for us, but let's go ahead and just take a little, little scratch paper over here. And what do we need? Well, we need to get a common denominator. Like this is arithmetic right here now, right? Well, what are we going to write here? Well, how about negative? How about negative 12 over 4 is the same as negative 3? Yeah. So then when we add that together, we get a negative 3/4. So this is just negative 3/4. So I'm going to write negative 3/4 here. Well, I get a perfect square. That's what I was going for. Even though it was kind of painful, it still gave me a perfect square, which allows me to continue to break this problem down. P minus 3 halves equals plus or minus. Well, it's a little nasty here, right? Let's do a little more work with this guy now. Over here. So I'm going to forget about the plus or minus for a sec. I'll put it right there so I don't forget it. I'm just going to concentrate on this idea right here. Okay. I think the very first step we can do is remember when you have a negative under the radical, let's call this that, right? Simplify it with the imaginary unit. Replace a negative under the radical with I, and that I is on the outside of the radical. And then the other idea is, let's use the quotient rule, which says the square root of 3 over the square root of 4, I. And wait a minute, the square root of 4 on the bottom, that's just 2. So we get the square root of 3 over 2i. Okay, well, that's simplified down at least. So that's what that is. So now we have plus or minus the square root of 3 over 2i. Okay, and then where are we at? 16. So then the last thing I want to do is I want to, of course, add this to both sides. So if I add that to both sides, I get p equals a positive 3 halves plus or minus the square root of 3 over 2i. And let's see. And that should do it. Let's see, I'm just double checking because I see I did a sleepy error on my paperwork over here. And I just want to make sure. In fact, there is nothing else wrong. Okay, good. That was just an error over there, but I didn't make an error here. This is good. So we've got p equals 3 halves plus or minus the square root of 3 over 2i. And why was that harder? Because of that little guy right there, right? That one right there, that odd number, because you had to divide by 2. Solve by completing the square. Same thing. Okay, solve by completing the square. Now, what makes this challenging is, darn it, that leading coefficient is not a 1, and that needs to be a 1 at all costs. At all costs, that needs to be a 1. So I've got to divide by 4 to make that happen. I'm going to go through and divide each term by 4, and this is going to make some, I don't want to say nightmarish stuff, but it makes the numbers worse too. So this is why we did it, so that's nice. I don't think I'd call 11/4 z nice. And then we've got this negative, right? This negative, or minus 3/4 equals 0. We got to complete the square. So this little guy right here must be legally moved over here. So we add 3/4. So I've got z squared minus 11/4 z, and I have a space. I added 3/4 on both sides. I've got a space. So now what do we do? Well, we're going to have to come up with that value of what's our little magic number, right? Okay, so we take, once again, like we did before, we take this nasty negative 11/4. We've got to cut it in half. Well, cutting something in half when it's a fraction is easier done by just multiplying by a half, right? That takes half of it, just like dividing by 2. So we're doing the same thing that we did before. So now when we multiply by half, we get negative 11/8. We get negative 11/8. Now this must be squared, which gives us, I'm going to write it below it actually, which then gives us a positive 121, right? I'm squaring it over 64. Wow, that is the special number that completes the square. So we've got this nasty 1. Oops, how did that happen? So we got this nasty 121 over 64 and 121 over 64. Okay, now what? Well, now, why did we do this painful experience? Well, because this is what makes this a perfect square. That's why we did it. And normally this is going to be a nightmare to factor, but remember, don't hurt yourself. It's right there, right? It's going to be right there. So in our procedure, we have the factored perfect square trinomial down to z minus 11 over 8, quantity squared. Now on the right-hand side, of course, we are going to have to, these are, I probably should put a plus symbol there. We added that, and we're going to need to add those two fractions. Well, to get a denominator of 64, our second fraction, 121 over 64, is good to go. But what did you do? You must have multiplied this 4 on the bottom by 16, right? So 16 times 16, so as just a little side note, right? 4 times 16 gave us a 64, and 3 times 16 is going to give us a 48 up top. So I just found an LCD basically. Now I'm going to go ahead and add those together. And when I add 48 plus 121 right here, this gives me 169 over 64. And I'm pretty happy about that because those two numbers are, in fact, perfect squares up top and bottom. So even after all that pain, I'm seeing something nice that's going to happen here. I square root the left because I have a perfect square. I square root the right. I don't forget my plus or minus. Now this gives me z minus 11/8 equals plus or minus. And you want to think about it as the square root of 169 over the square root of 64. So this just simplifies down to the square root of 169 is just going to be 13 over 8. Square root of 64 is 8. Now we add this to both sides, right? We add 11/8 to both sides and it gives us our answer. Z equals 11/8 plus or minus 13/8. Well, I know you don't like to add and subtract fractions, but those are, right, numbers that go together, right? Like terms, I guess you could call them, right? So I'm going to have to take 11/8 and I'm going to use a plus sign for this first answer coming our way. Z equals 11/8 plus 13/8, which gives us, what's that? 24/8. 24 divided by 8 is 3. So we get Z equals 3. There's one answer, and then the other answer comes from taking 11/8 and 13/8 and doing what to it? Subtracting using that sign. And 11/8 minus 13/8 gives us a negative, what is that, 2/8, which reduces down to negative 1/4. So z equals negative 1/4. And so we get two answers. We get two nice rational solutions. And by the way, because we have two rational solutions, guess what? This problem up here would have been much better to just factor it and set each factor, set it equal to 0, which it already is, factor it, and then set each factor equal to 0 and solve it. But they asked us to please complete the square for practice. And that was kind of a nasty one to practice on. And then look at this one, number 18. At least it's the last problem. Darn, I need that to be a 1, and what do I have? I have a 27. So I've got to, at all costs, turn that leading coefficient into a 1. So I've got to divide by 27 on each term. And even 0 divided by 27, but that's just going to result in a 0. So this gives us x squared. Well, that's good. And this is actually kind of nice because this is just minus 2x. And this is not as nice. 2 over 27 equals 0. Well, in terms of completing the square, we couldn't ask for nicer numbers. We're going to have to subtract this on both sides. We've got a negative 2 over 27. And I know I'm completing the square, so let's go through our procedure. Now this is looking pretty good, though. Negative 2, what did I say? What do you do to it? Cut it in half. That equals negative 1. Square it is 1. Oh, okay. So what color am I going to use? Purple. So if I'm going to add 1 completes the square there, I've got to add 1 over here too. Instead of just adding a 1, how about if we add a 27 over 27, which is also 1, right? And why did I do that? Because I know I need a common denominator anyhow. So on the left-hand side, we have a nice perfect square trinomial, which factors down to x minus 1 quantity squared. Remember, don't look too hard. Don't hurt yourself. It's right there, right, when you factor it down. Then on the right-hand side, we've got a negative 2 plus 27. So this is a positive 25 over 27. 25 over 27. And now we want to use our square root property by square rooting the left and square rooting the right, never forgetting our plus or minus. We've got x minus 1 equals, we use our square root property, or the quotient rule rather, which says you can square root the numerator and denominator. So this is going to be the square root of, I better write it down, right? The quotient rule is just telling us I could break this down to the square root of 25 over the square root of 27. So that's what I'm going to do. So square root of 20. So this probably should have been done as a little scratch work, I think, over here. So let's move it out a bit. I'm just going to go like this. So look at this scratch work here. Plus or minus, of course, that's 5 up top. What about 27? Well, 27 is just, that's a nice perfect square, right? Square root of 27, that's the square root of 9 times the square root of 3. Square root of 9 is 3. So square root of 27 is just 3 root 3. So I just simplified that down a little bit for us. So now this became this, which simplified to this. Oh, wait a minute, a square root in the denominator. We don't want to stop there. We don't want to stop there. We want to rationalize the denominator. So we can do that, remember, by multiplying the denominator by the square root of 3 and the numerator by the square root of 3. And that simplifies down to up top 5 times the square root of 3 is just 5 root 3. Don't forget plus or minus. Down below, we got 3, and then root 3 times root 3 is square root of 9, which is 3. So all of that simplifies down to 5 square root of 3 over 9. So wow, all of that stuff right there did take some work to simplify down. And now we're going to have 5 plus or minus 5 root 3 over 9. Oh, almost there, right? We have to add 1 on both sides to isolate the x, and x equals 1 plus or minus 5 root 3 over 9. And this is a rational number, and this is an irrational number, and those are unlike radicals, right? So you cannot put them together. So that's as far as we have to go. We are done with that problem, and we're done with this homework section. How awesome is that? X equals 1 plus or minus 5 root 3 over 9. And that is it. Hope that helped out. And you guys have a great day. And I hope everybody stays safe out there. Have an awesome day. Bye.